What I'm going to talk about is not what I do on a daily basis. What I'm talking about is a fairly theoretical talk. I'm expecting that a bunch of you will probably fall asleep, but that's okay, because you should wake up for the next 2 talks, which is going to be very practical, and it really talks about what we do on a day-to-day basis. Mine is a bit on the theoretical side, but hopefully you'll enjoy that as well. In terms of quick background about me, so I've been at this company for 4 years. Before this, I was an engineer at Facebook, and before that, I got my PhD in computer science from Carnegie Mellon. So that's sort of my brief background. Some things earlier this year led to the following talk, which is joint work with Arda, who's a PhD student at Carnegie Mellon, and Ravi, who is one of the deans at Carnegie Mellon. Okay. Cool. So what we're going to talk about today is recommendations. Recommendations are a part of pretty much any website that has this browse paradigm, right? So many of you would have seen recommendations everywhere. YouTube is a great example. So we have the main video in front of us, and there are a bunch of recommendations on the right, right? And in some ways, YouTube will not be YouTube if these recommendations did not exist, right? At least when I spend my time on YouTube, all the time, I'm basically looking at a video, clicking on something on the right, brings up another video, click on something on the right again, brings up another video, and that's like half an hour gone, right? So this is like an integral part of any browse website and an integral part of how users navigate the website. Okay, so that's what we're going to talk about, how to build these recommendation systems. Another example is Quora, right? There are plenty of such examples where any browse paradigm that you have, we're looking at a question about the most amazing photo that you've ever taken. And on the right, which might be hard to read, are other questions related to photos, right? Once again, Quora is the exact same thing. You start with one question, and before you know it, it's like half an hour gone just clicking these recommendations, right? Feel free to ask me questions in line, by the way. We don't have to wait until the end. Just ask me questions that you have. Cool. And since this is a search talk, and I'm giving a talk that's only laterally related, I'm going to claim that search is like recommendation. You have a query, and you have a bunch of results. That's like recommendations for your query, maybe. But let's not dwell on this too much. OK, so largely for today, what we're going to look at is how does this implementation happen, and how can we take this implementation that several times is online and convert it to something that's solved offline. Okay, so there are some notable exceptions to recommendations, like Netflix does this offline. But in a lot of cases, these recommendations are generated online. When you're looking at the page view, you're trying to figure out what are the best recommendations for this page. Okay? What are the most related pages that I can show the user? Now, you can ask yourself, OK, so that's great. But if I solve this problem offline, if I pre-compute recommendations for every single video in YouTube, can I do something more powerful? Okay, so that's basically the idea of this talk. Okay, so here's when we switch gears a little bit. And we're going to talk about a graph representation of recommendations. Every vertex on this graph is a video of YouTube. We'll use YouTube as a running example from here on, right? So every vertex of this graph is a YouTube video. And every edge is going to be a recommendation. Okay? So you basically have, in this case, let's see if I can get my mouse pointer to work. All right, so in this case, you have a video right there, which is the main YouTube video, and it has 3 recommendations. Each one of those videos have a bunch of 3 more recommendations, and so on. Okay, so you took the problem, which is online. You pre-compute all the recommendations, and we basically just have a straightforward graph representation of this recommendation. Make sense? And what we want to do is, now that this problem is completely offline, we can look at this graph and ask ourselves if this is a reasonable graph. Okay? If this is a reasonable graph, then your recommendation is doing a great job. But if this graph has really bad properties, then maybe you want to go back and redo your recommendations. Okay, so that's basically the crux of this talk, which is you do this pre-computation offline. You have this graph in front of you, and you can basically ask simple questions like, is the graph well connected? Can I efficiently browse it? Which is, if a user lands on one of these nodes, can they efficiently waste time? Is basically what we're trying to get to, right? And in this case, this graph looks great. Maybe it has some dense subgraphs, but it's very well connected. You can go from one video to another pretty nicely. And so it's probably a good recommendation system. Okay, go for it. Oh, no, so this is very high level. It's like hand wavy. There isn't a formal definition for what it means to be efficient. But we'll talk about some examples of what would be bad graph structures to have. So that sort of gives you a feel. Okay, so that's basically what the next slide is, which is, let's say that in this graph, I have these sorts of high density subgraphs. Okay, so these are like clique-like subgraphs where once you get in, you can sort of very hard to get out. Okay, this happens to me a lot on YouTube. And if you guys have spent anywhere close to as much time on YouTube as me, you probably know this feeling, which is you start with the topic, which is something like hole-in-one golf videos, and you go watch a video. It gives you a bunch of recommendations on the right, and you start clicking the recommendations, and pretty soon all the recommendations on the right are videos you've already seen. Okay, and so you cannot sort of waste more time basically at that point, which is you have to start thinking now, okay, so I'm done with hole-in-one in golf, what do I do next, right? Ideally, it should be a case where it's like seamlessly I'm just browsing, spending lots and lots of time without getting stuck anywhere. Make sense? Even worse than that are these sorts of vertices, which is any of these isolated vertices where nothing recommends these videos. Okay, and in fact, it's a fairly simple question to ask. Let's say, your company, wherever you're working, has a certain recommendation system for your website. I can ask a fairly simple question, which is, how many videos are not at all recommended, period, by any other video, not at all recommended by any other page? Is that number 50%, or is that number 10%? And most people would probably not have an answer, right? Unless you do this offline, you probably don't have an answer as to how many videos are not even recommended by a single other video. Okay, and I would not at all be surprised if this number is as big as 50%. Okay, 50% of your items not recommended at all. And the last one I want to talk about are loops. So which is video 1 points to video 2, video 2 points back to video 1. Okay, it's a very usual scenario. It's a very real world scenario. And this is just me trying this on the first attempt to prepare slides. I watched a video, and that recommended me a second video. I watched that video. It recommends me back the same video that I started off with. Okay, that's like a complete waste of a recommendation, right? YouTube knows I just watched the video. What's the point in showing me the same video that I just came from, right? And that's like a simple situation where you can just avoid this whole recommendation system. If you have it offline and you see one of these loops, it's fairly simple that you're not doing a great job there. Make sense so far? Okay. Cool. So for today, this is close to the hard for Bloom Reach as well. But for today, what we're going to focus on as a theme is how do you prevent items from not being recommended at all? Okay, very simple question. The most basic question you can ask in these systems, how do you make sure that every video is at least recommended by someone? It's like the most fundamental of questions you can ask. If you can answer that, then you can go build more on top of that. Okay, very simple question. How do you ensure every video, every item is discoverable? That's it. Okay. So what we're going to assume is that there are two phases in this recommendation system. The first is a pure relevance-based system, okay? And we're not going to talk about that too much, but that's a system that hopefully people have, which is going to retrieve about D recommendations. And then the second phase, which is what we are interested in, is how do you take those and get a subset of them such that the resulting graph is nice? Okay? So basically, you have a relevance-based engine that's going to give you 1,000 recommendations. Now, how do you go from that 1,000 to a 10 so that the resulting graph is pretty nicely connected, has this efficient browsing pattern to it? Got it? Okay. Okay, so here's where we're going to start switching gears a little bit. And we're going to go into parts of things where it's probably helpful to recall undergraduate sort of senior year algorithms classes. But if not, I mean, I think don't worry too much about it. But I think it's a little bit interesting to follow some of the theory. So here's what the graph is going to look like. So we have a graph G, where every vertex has an out degree of D. And we're going to get try to get a subgraph G prime, where every vertex has an out degree of C, which is less than D. Okay? Same problem. I haven't changed a thing so far. And so what do we want to optimize for? So we want to, it's natural to make sure that the graph is connected. Natural to ask that every vertex of the graph has an in degree of 1, which basically means every video is at least recommended by one other video. That's all. Okay? Very, very simple constraints. How do I make the graph connected, which in turn actually implies that every vertex has an in degree of at least 1. That's it. Very, very simple, right? And if you recall, if C equals 1, which is you take this graph, every guy has an out degree 1 and in degree 1. Okay? Every vertex has an out degree 1, in degree 1. This is like a Hamilton cycle problem, which turns out to be NP complete. You might recall this. If not, it's not a big deal. Okay? So instead, we're going to look at a slightly relaxed version, which is a little bit of a generalization of the problem as well. Okay, so which is we're looking at a bipartite graph instead, where the left side is L and the right side is R. And the left side is basically the list of all the popular items you can think of. And the right side are the list of all the items that you want to get discovered, right? So in YouTube's case, the L could be all the top videos, like Gangnam Style videos on the L side. Nobody needs to discover it, everybody knows it. On the right side are things that you think people should find are interesting, you want to promote them somehow. That is no reason why every video cannot be on both sides. You can take every single video, 100 million videos, let's say, put it on both sides. That's perfectly fine. Okay? But if you want a generalization, you can keep L smaller, keep R smaller, put the video only on one of the two buckets. Either way is fine. Okay. So we have a bipartite graph G. Every vertex on the left has out degree D now. Okay? So left side is going to recommend stuff to the right side. Same problem as before. We want a subgraph where left side goes from degree D to degree C. C is smaller than D. So you start with 1,000 recommendations on the left, bring it down to like 10. Okay. Same problem as before. We want to maximize the number of vertices with an in degree of at least 1. So no change so far, right? It's the exact same problem as before. And this formulation actually has a lot of polytime algorithms. People might recall if C equals 1, this is actually the case of bipartite matching. Okay? Again, undergraduate algorithms, probably everyone did bipartite matching. If C is larger, it's the problem of fractional matching, which you can map it out to actually bipartite matching back again. And there are lots of solutions. There are lots of max flow-based solutions, lots of other dynamic programming-based solutions. But the issue that I want to think about is the following, which is, let's say, again, hypothetically, you're a software engineer and your company has a recommendation system. And basically, your manager tomorrow comes up and says, just try to make sure that we don't have videos that go unrecommended. That's it. Okay? So you have a bunch of videos on your site or a bunch of pages on your site. You just want to make sure that no video goes unrecommended. It's a very simple request. Right? From a manager's standpoint, it's like a pretty simple request, and hopefully you're done by the end of the day. Right? Now, the only tool that you have to solve this problem actually is one of these max flow-based solutions, okay? Which is, if your code is poor enough, like mine, then it goes to thousands of lines of code. Of course, if you use Java, you start with a factory, and by the time you get down to like interfaces and whatnot, by the time you get to even the algorithm, it's like a few thousand lines of code, right? So that's the only tool that you have to make sure that this is the case. That's it. All that you're looking for is making sure that no video goes unrecommended. And you need a MaxFlow solution for this problem. Okay, so that's the problem that we're having. So if you are lazy and you said, well, that's what my manager asked me, I'm not going to bother with it, I'm just going to pick a few recommendations, just arbitrarily. I'm just going to pick literally C recommendations randomly. How bad can things be? Okay, that's basically the idea. It's like manager comes, asks you this question, you're like, okay, whatever, I'm not going to do it. I'm just going to pick C randomly. How bad is my solution? And believe it or not, this is roughly kind of sort of what happened, and it turned out that solutions were pretty good, and I was pretty surprised, and that's basically how this whole thing started. So we're going to switch gears once more, but it's just literally like 3 slides, but it's going to be like some amount of analysis, but it should be not hard to follow. So here's the underlying model that we're going to assume, which is we have this bipartite graph G, and every vertex picks d random edges out of it. Okay, so that's the underlying graph. Every vertex picks d random edges, and my algorithm, all that it's going to do is pick C out of the d edges arbitrarily. It's just going to literally pick the first C edges. You're done. Okay, so that's the graph we are looking at. We're looking at a bipartite graph. Every vertex on the left has C degree, and you're looking at how many videos got unrecommended, not even recommended once. Okay, so this is the one slide that has the analysis. So, and it's actually not hard. Okay, so I think at least I thought it was kind of cute that it's fairly quick to do, and it is actually insightful. So here's what it is. Okay, so we are going to look at all the videos on the right side. These are the videos I want to recommend to. Okay, and I'm going to have a random variable xv to be having a value of 0 or 1. 0 if nobody recommended this video, and 1 if even one other video points to this video. Okay, very simple. xv is 0 if nobody points into video v, and xv is 1 if even one person points into the video. So straight up combinatorics, what we want is the probability xv is 0, which is not a single video points into me. Okay. Now if I look at a single edge, just one edge, the probability that that edge falls on me is 1 over r. It's 1 over all the videos. What's the probability if I look at an edge, that edge is pointing to me? It's 1 over my competitors, which is 1 over r. What's the probability that that edge actually does not fall on me? Is 1 minus 1 over r. Okay. So we're doing that right there. 1 minus 1 over r is probability a single edge does not fall on me. What's the probability none of the edges fall on me? Is 1 minus 1 over r raised to the number of edges, which is CL. Right, that's the probability that every single edge misses me. It's 1 minus 1 over r raised to CL. This doesn't matter really, but that turns out to be almost the same. 1 minus 1 over r to the CL is e to the negative CL over r. Okay. Now let's keep that aside. Now we're going to have a variable x to count the number of videos that got recommended by at least one person. So x is summation xv. It just counts the number of videos recommended. Now what we want is the expected number of recommended videos, which is e of x. That is e of the summation of xv, which is just straight up there, which is summation of e of xv. That's by linearity of expectation. It doesn't matter so much, but here's the last part that we need some attention, which is e of x now, which is the number of recommended videos, is cardinality of r times 1 minus e to the CL over r. Okay, so let's parse that a little bit. What we just did was e to the CL over r is the probability that my video, one video that I'm interested in, got 0 recommendations into it. Okay. 1 minus e to the CL over r is the probability that that video got a single recommendation at least. So the total expected number of recommended videos is simply the number of videos in all times the probability that a single video gets recommended. So it's cardinality of r times 1 minus e to the CL over r. Okay. Is that kind of clear? Now, the interesting thing about this is this ties in all the key parameters of the problem. It ties in the relationship between C, L, and R. Okay, so these are the three key parameters that dictate whether I can get away with being lazy or not. Okay, and we'll see why that's the case in a bit. Now let's look at what MaxFlow would have done. If I went in and implemented the best possible algorithm, we can look at what that would have done. That's a much easier analysis, or at least the upper bound we're using, which is there are only CL edges in total. So the number of recommended videos cannot be larger than the number of recommendations itself. That's CL. Number of recommended videos cannot be larger than the number of videos itself. That's R. Okay? And so the best possible solution cannot be larger than the min of the number of recommendations and the number of recommended videos. That's straightforward. So my final solution is right there, which is the numerator is basically our solution. Denominator is basically what the best solution could possibly be. Okay? Now, if that ratio is very close to 1, we are in great shape. If that ratio is like 0.01, we are in pretty bad shape. Okay? So that's basically what this comes out to. And so that's how that curve looks. On the y-axis is accuracy, on the x-axis is CL over R. But ignore the curve for a minute, because I'm just going to explain the significance of what this is. Okay? Now let's say that I'm YouTube. Okay? Let's say I'm YouTube. And this is basically the result of this talk, right? So let's say I'm YouTube. I have 100 million videos. And I'm solving this recommendation problem. Okay? On my left side, I have 100 million videos. On my right side, I have 100 million videos. I have 10 recommendations per video. My solution is going to have an expected value higher than something like 99.99, probably a few more nines, as good as what the MaxFlow can give me. Not even close. Okay, it's like not even close that you would want to implement something else, right? And this is a one-line awk command that you can implement, or a one-line Python command that you can implement. It's like one-line Perl command that you can implement. That's going to take like maybe bytes of memory. Okay, definitely less than 1 kilobyte, but probably in the bytes. In comparison, the other tools that you have is this MaxFlow formulation, thousands of lines of code probably, if you're bad enough. 100 gigabytes of RAM, it could easily take. You have to figure out how am I going to scale this across Hadoop jobs, whatnot. But compare that to a single line of awk command. That's it. And the amazing thing is, if let's say that, going with the same example, 100 million videos, let's say that your left side and right side are the same. You're looking at 100 million videos recommended. Even if you have 5 recommendations per video, pretty much with 95.9%, you're fine. Okay? Even with 3 recommendations, you're actually fine. Okay? It's only the case when you have 1 recommendation per video and you have 100 million videos to recommend. That's when you hit the bottom, which is about 63%. That's how it bottoms out. So when CL equals R, that's the worst possible thing. That's 63%. If CL is much greater than R, your left side is much greater than right side, you're totally fine. If your left side is much smaller than right side, it's totally fine. If CL equals R, that can also happen in a second way, which is you have 10 million popular things on your left, 100 million videos on the right, 10 recommendations per video. That still gives you only 63%. Okay, that's bottoming out. CL equals R. Okay. Any questions? Oh, good. So circularity within a single video, you can take care of it just by making sure that doesn't happen. But you still have loops. So that's an excellent question. And so the question was, how does the circularity get taken care of? How does the cliques get taken care of, right? And it's a great question. And the reason it's a great question is, initially I flashed a slide that said the problem was NP complete. Then I flashed a slide that converted it into bipartite graph, and I said there are polytime algorithms, right? So what went wrong? And basically, I didn't want to go into the details, but what went wrong is the solutions here do not basically address the cliques. The solution here does not mean that the graph is actually connected at all. You can cover the graph with a bunch of cycles. Okay, that's the difference. Covering the graph with cycles is actually polytime. Covering the graph connected becomes hard. So to answer your question, we don't actually deal with that, basically, which is why I started off by saying the only thing we will talk about here for this talk is basically just making sure everybody gets at least one link into it. That's a great question, though.
Excuse me, on this side you have less than 0.1. Did you really mean it, or did you mean less than 1?
Oh, 0.1 is fine. So basically what's happening is, so CL over R around 1 is when it does the worst, right? So it's going to get an accuracy of more than 95% if CL is much lower than R, in this case less than 0.1. Or if CL is much greater than R. So basically the line here is CL over R. So if you're below 0.1, you're here, basically. And if you're above whatever that is, 3, you are right there. So your accuracy is high on both sides, but around that is kind of low. Cool. So that's all great, but ideally you want to go beyond non-uniform probabilities. And that brings up actually quite nice graph models. That brings up actually very practical models that you can think about. And here is one that we are working on, which is let's say I'm looking at Quora questions. Okay, that is an underlying ontology of Quora. Either you see it or you don't see it, but there is an underlying ontology of Quora. So let's say I'm asking a question about why does my web server behave a certain way when I'm using Pylon's framework in Python. Okay. With a high probability, the recommendations are going to be at the leaf level of this ontology, which basically means there are other questions around Pylon's framework. Okay. With an exponentially lower probability, you can say that you go one level higher on this tree, and the questions are about Python. Okay? And with an exponentially lower probability than that, the questions are around software engineering. And with an even lower probability, the questions are maybe anything else. Okay? So you have this underlying tree, and basically your underlying recommendation graph can be generated from this sort of probabilistic model, which is pretty close to reality. And so you can think of how these arguments extend in those cases. You can think of multiple recommendations. We just talked about the case when every video gets recommended once, but you can ask, what if every video needs to get recommended twice? But the most exciting part of this is when you have these edges that are weighted. Okay? And the reason this is kind of exciting is basically, let's say we are YouTube. Okay? Now this gives us immense power to control the entire flow of traffic across YouTube. Okay, let's say again, I am like one of the videos is this Gangnam Style video. That video pointing to a new video immediately means that the new video is going to get a ridiculous number of views, right? I have some other lectures on machine learning. If those lectures point to these videos, you're going to get no hits, basically. So, but the amazing thing is these are like in some ways like rivers, right, in this entire website. And these recommendations pretty much govern how the entire traffic is going to flow across all of YouTube, right? And so once you have these edge weights that say, here is the number of views this adding the single edge is going to give you, and you look at this graph overall, now you can pretty much dictate how your entire traffic for YouTube is going to flow once a user lands. Okay? So that's like a pretty powerful notion where you can take this recommendation system and you can basically say, okay, so here's my complete graph going to look. Based on whatever you want. I want certain videos to be promoted, certain videos to get too many views right now, I'm going to ding them. I have a certain bunch of videos, I don't know if they're good or bad, so I want to experiment with a bunch of views for them. You can put all of these as constraints, actually come up with a nice graph that actually dictates pretty much everything that goes through the website. Right? It's kind of powerful. Even if you didn't follow all of it, the major takeaways, a couple of things, even going beyond recommendations is, you can always ask what's the advantages of thinking of problems from offline standpoint as opposed to always online. As I previously said, people do recommendations offline as well, but we can think of search results. Would you show the exact same search results if I could pre-compute all the search results? If I knew the results that I'm going to return for all the search results, would I always give the same results? Okay, or would I change the results? Can I do something better there? We can take an online system where your query is done online, results are generated online, take it offline and see would you do the same thing if you knew ahead of time you're going to get a bunch of queries. The other thing that I can think of at a higher abstraction is keeping things simple, right? I mean, software engineers know this. When you write algorithms, when you do distributed systems, you don't want anything complicated. especially true when you're doing these things. And it's great to just try something. It doesn't have to be a full-blown analysis, but try something. If that works, then you're sort of pretty happy with it. So keeping it simple, being lazy is actually kind of sometimes a good thing. So that's pretty much all that I had. So we're kind of doing okay on time. I think it was about half an hour. We're trying to keep all of us around half an hour. So I could take a couple of quick questions if people had. Otherwise, we can bring the next person over. Let me swap the slides meanwhile. But if you have any questions meanwhile, go for it. If you don't have questions, no problems either. Go for it.
So why do you think a graph is the main method for doing recommendation and many other methods available?
Yeah, so of course. So there are lots of methods to do recommendations, right? And when people talk about recommendations, usually they talk about getting high accuracy in terms of having the recommendations. So Netflix challenge and things like that, it's basically focused on something else as opposed to what we were focusing on here. So there you're much more, you're trying to optimize relevance, right? So then certain techniques make a lot of sense, which is trying to make sure that your movie preferences that you show someone is something that they would definitely enjoy. That's kind of the biggest question you're asking there. But that's not what we are saying here, right? I mean, what we have is a certain cutoff on relevance, and then you're asking, how do I make sure that I spread my traffic across all the pages on my website? Which is kind of a different model than the typical way people think of recommendations, which is much more on the relevant side rather than on the making it more socialistic side of traffic in some ways, if that makes sense.
If that comes to why do you care about people discover every video?
That's a great question as well. So why do we care about people discovering every videos? So the answer to that is could be a few different things. One is in the video case, it's a little bit easier. But there are always issues where you don't know what you have is good or not. Okay, and this is beaten to death in the ads community with this exploration, exploitation, and all that stuff, which is you want to try to figure out, if I gave it some traffic, can I measure some signal and make sure that if that's actually a good thing or not. If you don't have any traffic, you don't have any signals, and if you never promote these videos, you never have any signals, and these videos will basically just stay where they are. So that's sort of one reason why you might want to promote certain videos that have no views. The other reasons are just trying to make sure that if there are good content, they sort of get discovered, and there's no artifact that's preventing you from discovering that content. Especially in like these online recommendation cases, there could be lots of artifacts. Let's say some page has a high score for a certain feature, whether it's page rank, whether it's the number of links pointing into this video. And whenever you break ties, these videos keep coming on top. So there might be a subset of videos that get ranked very highly at the cost of everybody else even getting a single recommendation. So those are some sort of reasons why you might care about it. There are certain reasons why Bloomreach cares about it, but that might be a little bit more on the confidential side, if that makes sense. Cool, yeah.
How does the learning affect, for example, if the user is seeing a video and stops in like few seconds and goes to the next part? So it's more of a dynamic behavior and it's adaptive to learn.
Yeah, absolutely. So those are all features that you might want to build into your recommendation system more on the relevant side. Like I said, so if they viewed the video then bounced immediately, I am tempted to think that it's actually a pretty bad signal. You definitely don't want to recommend that video back again, especially when they look at the next video. But it also goes back into this exploration, exploitation kind of question, which is, let's say you start sending a little bit of traffic to a video and it starts performing pretty badly. Do you want to change things up? Yeah, I mean, those are go into much more of the relevance bucket than this sort of an optimization kind of bucket, if that makes sense. Yeah.
When you want to maximize the expected value of the length of the path, is that kind of what you're doing, or is that something different?
Oh, we're just maximizing basically the number of videos that get at least one recommendation. That's basically what I presented, which is just maximizing the number of videos that get recommended at least once. That's
This would be a different problem.
That would be a different problem, yeah. The extension is you can set a threshold and say, what would I do if I want every video to get recommended at least a certain lower bound number? And then you can say, what if I want every video to at least get a certain amount of views? It's a lower bound. Above that, you probably don't care. You want other things to take merit, but you want a lower bound. So those are the sorts of problems that we're working on here. Cool. Yeah, let me take last question and then we can switch over. Yeah.
So do you try to mix these offline methods with online methods?
That's a great question, and I mean the short answer is you probably want to do something along those lines, where you have some of these offline methods. Lots of things could change between the time you ran this, put it into production. The video gets taken down. I mean, you probably don't want to send any more lower bound traffic into that video. So definitely you want to mix a certain amount of this online and offline. So yeah, so depending on the application downstream, that could make a lot of sense. Cool, thanks so much. Let me get the next speaker before it's too late. Thanks.